I'm just curious, how many of you have any knowledge about deep learning? Some. Nice. And about reinforcement learning in particular? Yes. Yeah, I mean, deep learning is getting more and more attention, and that's okay, that's great. But reinforcement learning, for some reason, is still more obscure. So, but it's amazing. So I want to try to convince you about that. So in this talk, we are going to have mainly 3 stages. First, I want you to introduce reinforcement learning. What is this about? Why it is important? Why Elixir? Why Elixir will be a good option for implementing this? And at the end, I'm going to show some existing tools out there, not in Elixir, and then some coding examples by myself. There are many problems in the AI community that was thought to be out of reach for years, and they are constantly being solved by this technique, by reinforcement learning. And as you can see from the definition, reinforcement learning, RL, is suitable for goal-oriented problems. Yes, where an agent learns from direct interaction with the environment, get experience from that, and then figure out how to achieve the established goal. It is fundamentally different for supervised learning and deep learning, in the sense that the optimal policy, and policy here is the rules that an agent is going to take to maximize the reward or achieving the objective. In these setups, we have no idea what the optimal policy is. So we cannot give directly examples for a neural network, for example, to learn for. So that's a big difference here. And I'm going to show you this example about, here, for example, we have this environment. It's just a guy trying to walk, and the goal is to advance as much as possible. The reward of how well the agent is performing is measured about how much it can advance in the less time possible. And what you are going to see are a set of trials, because this guy has no idea how to even do anything. So yeah, I start like that. So eventually it starts finding some policies, some combination of actions that at least allows him to advance just a little, and it keeps improving in a very weird manner, but so it can also learn to fly. So this is amazing, really. Oh, shit. Because we only put the rules about the environment and the effects the action have in the environment, but we don't need to give any further example. So everything is obtained just by experience, just by interaction of the agent with the environment. And you see, there are so many applications on video games because it's easy, because the setup is already established. There's a clear goal, and there's a way to quantify how well the agent is performing. So now we can learn to play games like this very easily with reinforcement learning. One of the big news some years ago was about the game of Go. It was one of the milestones in the artificial intelligence community, because we assume that maybe the kind of patterns could not be extracted by a machine, and it was a human ability to understand this. And it happens for the first time that a machine using this technique defeat the world champion. So these are the main components of reinforcement learning. There's an environment that has a set of rules by itself. There's an agent that can observe this environment and be aware of the current state. The environment can give a reward signal to the agent in response of their actions. And so the agent can take these observations and these reward functions and start to figure out how to perform better. The agent is the component that takes decision, and only that. In our first example, all the guy itself is part of the environment. The physical aspect of the agent is part of the environment. The agent is very abstract, and it only takes information, learns how to do, and take decisions. And the environment can reward the agent by its action, and constantly the agent is able to observe the environment and how it changes. All the theory about reinforcement learning is based on this assumption, which is the Markov decision process property. And it means that it doesn't matter what happens before or how we get into a particular state. It really doesn't matter. What matters is actually the opposite. What is going to happen? What actions can I take that give me to some states, and which actions can I take then so I can maximize this reward I can get? So in any case, the optimal solution is defined by this expectation formula here. This is expanded this way. This is a mathematical expectation, which is the values, the product of the values and the probability of each. And what we are saying is that we are weighting the probability of the next state given current state and actions, the immediate reward function and the same function, but evaluated at the next step. So it's like dynamic programming to the future. And this is the expression that we really want to maximize, which will be this approximation of the future reward we can get. Technically, this is expected cumulative future discounted reward. Cumulative is because on each action we are accumulating the rewards. It's discounted because we have a factor here that makes less important actions to be taken in the future and more important the actions that are being taken now. This part of learning has been very successful thanks to artificial neural networks, because maybe we can get this knowledge in a table or something like that, and that works if the number of states of the environment is fixed or discrete and small. But in some cases, most of cases, it's not. So neural networks are great universal function approximators. So we can get as input from the environment even images. We can actually understand what's happening in the image. And so for video games, for example, we can take the raw output of the game, the screen, and learn directly from that, and learn either the expected future value or the policy itself. And it's usually very GPU intensive. And yeah, Elixir maybe is not a good option for doing GPU operations. So why Elixir then? And there are many reasons. Even if we use, because we don't need to, even if we use deep neural networks for the learning step, all the rest of the setup is very CPU intensive. The rules of the environment are particular to the environment. The logic of the reward is also unique. So the entire setup is more CPU intensive, more than GPU intensive. So having the ability to use multiple cores is really important for this. Also for IoT, or having the ability to deploy this kind of learning in physical systems. Again, video games are very easy problems. They are fixed and they are isolated. But if we want to implement reinforcement learning on the real world, we need to have sensors of what's happening, to have a representation of the environment, for example. We need to communicate to the agent if it's going to take some action, some physical action. So I'm excited with Elixir because there are projects, as you may know, like CRISP or NERVs that are going very well for this. So that's one reason. And the actor model itself is very convenient for this. If we are going to set up this in a physical system with many devices interacting with each other, it's very natural to have the actor model ruling all this. There are some tools out there. I selected this by importance. So just a quick look. First one is GEM. I think this is by far the most popular of any, because mainly is a defined interface to communicate with the environment, and has many implemented environments. Many of them are based on Atari games, so you can directly start coding and interacting with video games using GEM. But maybe this set of environments is limited, so there are other libraries like ML agents by Unity, where you can have environments in a 3D world. But any of this helps you to actually do the learning. It's just an interface to interact with virtual environments. So for actually training something and learning a policy, we have Dopamine, a project by Google. You can see here is a typical setup of the entire experiment. Everything is based on a lot of configurations. You put all the parameters there, which environment, which agent you want to use, etc. And the code looks like this. It's very, very tied to TensorFlow. So if you don't want to TensorFlow, you will need to do a huge code rewriting. And it's also very limited in this set of agents it can perform. It is not very modular. So, and also it's a research framework. It's not intended to be used on the real world. And the community is okay with that, because most of the people that is aware of reinforcement learning, they do research and run benchmarks, so this tool is enough for that. But taking this for production on real problems is not that straightforward. So Facebook Horizon tries to do that, like how to actually set up the entire experiment even in a distributed manner. But actually, Horizon is like a set of scripts for interact for other third-party projects like Spark. So it comes from the official documentation. That's how this framework is supposed to be used. It's not a framework at all. It has no defined components. It's just a way of glue independent projects for RL setups. Taking that into account, I started to implement some of these components in Elixir. Maybe at this moment it makes sense to you that each of these components, like the environment, should be a process and potentially agent server process. So I started this. I just put it a name with an X at the end, as we like it, and make it a logo. And the core components of this is actually the definition of the environment, and it can be done with the behavior. So what we need from the environment is just to expose these functions. We need a way to observe the state of the environment, but this observation may not be the same as the internal environment representation. It is just the abstraction of that original state that the agent is able to see. Reset, just for resetting the environment, and the most important function, this one, step. That's the interaction point of our agent. The agent just take an action, send an action to the environment, and we get an experience piece back, which is the recorded information about the state, the action taken, the next step, and reward, and also a termination signal. Because there are many problems that are episodic, like maybe chess. You take decisions, but it's until you win or lose that you can get the reward. So, and it's then when the episode finished. So that's that termination signal. In info, you can put whatever else you need. We also require for the environments to define these two spaces. These are actually the real interface. Like, we need to define how the observation space is going to be defined. It can be as simple as a discrete space. If we have a finite number of states, we can enumerate, so a single number can represent that. And then by utilizing protocols, we can have different ways of sampling a random action or a random observation from this space, or check if some given action follows the rule of the action space. This is a very particular implementation of an environment. Here, everything is about to get from here to this G, that is a goal, without falling on these holes that have H. So in each of these discrete states, we need to take a decision about where to move. We give it a step, and we get an experience piece by that. I forgot to play it from the beginning. But yeah, you get the idea. And I also have this special environment implementation, which is actually a wrapper for BEAM. So it exposes exactly the same as an environment. It follows this contract of the behavior, but actually all the logic is performed by BEAM. So this process actually creates another Python process to communicate with. And part of the internal state is the environment object serialized. So it's part of the Elixir environment. So it's not necessary to have the same Python process alive, because I can get another one, send the environment, do one operation, and get the response back. And it's pretty cool because you can concentrate in just making experiments on the learning, utilizing existing and widely used environments in GEM. And because it's possible to make this interaction, I'm doing this with Airport. It's also possible to run even neural network trainings on Python machines. There are plenty of tooling for neural network on Python, so it can be used for that too. No way, I forgot again. Okay. Anyway. And our agent can just do this, receive this information, this state, action, reward, next state, next action, make whatever to incorporate that knowledge and learn something. This is a very basic example. And so we can get this knowledge representation on this form, each of the states, and for each of the possible actions in our previous example, scored by how good it will be for maximizing the reward. And I'm putting here the names of the models of where they are. This is a very important one, a replay memory, because it is possible to just take the current experience directly for interaction, make something with it, and just forget about it. But I'm going to explain why having a separate memory buffer for that is a good idea. And again, we can just establish the contract of this memory buffer. And so making this is important for many reasons. Mostly for gradient-based methods like deep neural networks. It's very important to have independent and identically distributed data. So we require that our sample is as uniform as possible in order to counteract some temporal bias on the weights of the network. And also, it's also very hard to evaluate how well my current policy is if I'm changing it at the same time. It's really hard to converge without that. So it is common practice to fix a policy, get some data interacting with the environment with the current policy, and then get all those experiences, update the knowledge, and start again. So replay memory allows us to decouple completely the learning phase with the environment exploration. And one of the most exciting stuff around having a replay buffer is depicted in this article. It was made just 1 year ago. 1 year ago by the leading company on this, which is DeepMind, using 7 of their top scientists. And they just show that we can achieve something like horizontal scalability on training by making multiple copies of the agent and the environment, because we need that. We just need to explore as much as possible how the environment is going to respond and what rewards we are going to get. So we are not limited of having just one at a time. So we can just spawn as many copies as possible. For example, our actors, each with a policy. You can change them asynchronously, but all of them, by interacting with the environment, deposit experiences in this replay buffer, and the learner just has no communication with the actors anymore. So it's just with the replay memory. And from the perspective of the learning, there's no difference. If we have a deep neural network getting experience one by one in a temporal manner, or from this buffer, it is exactly the same. And we have a lot of benefits. You can see here, for example, this is the improvement over time having few copies comparing with having a lot. So it's just if you have resources to make copies, do it. It's a good idea. And it is actually done a lot, even on physical systems. So it's common practice to do this stuff. At least conceptually, all we know this is needed. But again, there's no tooling for doing this. I really want to stress out the importance of creating this reliable set of tools for not only fast prototyping this kind of setups, but also for deploying in the physical world. Because reinforcement learning has a huge potential for transforming society. Virtually any decision-making process we have can be optimized by this, every single one. And what we have learned from this kind of techniques is that we may have a very convincing approach for solving something like chess, for example, or Go. We as humans have our way of interpreting this, and it is amazing to have a tool that can show us that it can do better.
So when we start training the model, whatever we developed, the accuracy of the model will depend on how accurately we model the environment, because we are not training the model in the real world. We are actually using the environment which we created virtually to train the data. Like the example of walking. So we actually made the model using, we actually did not use, as you said, sensors or anything. We actually modeled the whole thing ourselves. So is it good practice to make the initial model virtually and then put it out in the open and then train it, or what exactly is the practice there?
Yeah, it is. Even on this picture, we can see just a limited amount of physical copies, but there are thousands of copies running virtually. That's an entire topic by itself, which is transfer learning. Because even if you can model very well your physics and all that, there's a difference. But anyway, it's better to have a lot of experience on one environment that is very similar to the real one, and so you can transfer a lot of knowledge from there.
What is the difference between deep learning and reinforced learning, in a nutshell?
Yeah, deep learning is a passive learning. So your network does not participate in the data acquisition. It's just going to try to maximize the loss function you put, but you decide which experiences or which data is given to the network. And this setup is intrinsically active. Your learning process is tied with the environment exploration. So there's a big difference in that sense. And the other one is, again, the objective-based nature of reinforcement learning. You are not giving to the machine examples on the solution you want because you don't know it, or you want to get a better one. You just put the objective, and everything is learn by interaction.
Why did you particularly choose, Elixir for your implementation? Like, what you highlighted is that basically one of the reasons was scalability, so that you can fire up multiple processes with Elixir. But how would that compare to say to Python frameworks like Greenlat or Async.io, or there are multiple frameworks in other programming languages that basically give you the same as you have in Elixir, where you can just fire up a set of instructions in a process. So I'm interested, is there any other reason for Elixir there, or?
More than the one I mentioned, I don't think so. I feel, again, the actual model is just very adequate. It's just very natural, and yet there are more options of languages and frameworks implementing the actor model. But it's this set of simultaneous advantages. For me, it's very important to having the ability to deploy this on the real world. So the existing Python alternatives are excellent if you are doing just research. So you have your set of benchmarks, and you do some modifications, and your setup never gets out of your workstation. So it is very important to have a natural way to deploy these components that are going to communicate in physical devices. And as I mentioned, I'm very excited about nerds and grades for this.
How much math somebody needs to learn to successfully employ reinforcement learning?
That's hard, because I can say maybe not much, but I'm a mathematician, so maybe it's not fair, my opinion in this sense, but it is possible. I mean, on any technology that now developers can naturally use, there's a lot of theory behind, but it can be abstracted. And that's something that also is missing. You need really get into the details still with existing tooling to actually do something just for research purposes, and then take that out to the real world. It's still a long way to go. But I think having this natural way to compartmentalize all the pieces and having independent processes makes all the picture a lot easier to understand and implement.